Okay, let's take a look at gases. I know in the last notes on the kinetic theory, we talked a little bit about gases, but there's a little bit more to it that we need to cover. So the first little piece of these notes are kind of a review a little bit, but gases, remember the molecules are constantly moving. The gases that are inside this room right now, they're all bouncing all over the place. They're always moving all over the place, right? There's no attractive force between them. So I always like to say that if this is an oxygen molecule and this is a nitrogen molecule that's in this room, they aren't attracted to each other in the idea that they're pulled together, right? Nor do they like move like this, like fish, right? They're just bouncing around randomly all over the place and there's no attraction to them. Also, between the two molecules, which I said in the other notes, what's here in between besides me is nothing. There's nothing there. And it's not air, right? That's a common mistake a lot of people think is, well, yeah, okay, this is a particle here, there's a particle there, where there's air in between. But no, we're talking about these particles are the air that's in the room, right? In between, there's nothing. And actually, I alluded to this before in one of the other pieces of notes, but that is that 90% of this room that I'm in right now is absolutely nothing. Only 10% is actually air. So if this was my room, all right, there's the outline of my room, and that means we could take this wall and push it all the way over to there, all right? And this right here, that would be all the air that's actually inside this room, right? All the rest of this area, that's all empty space. There's nothing there, okay? Now you might go, Mr. P, how in the world is that true? Okay, let me write down, this is 10%. But you probably have heard that, well, but 79% of the air is nitrogen and almost 20% of the air is oxygen. Well, that's true. And what it is of this 10% area over here, 79% of this is nitrogen. So all of this around here, that's all nitrogen. And this spot up here, that's oxygen, right? And then there's just a little bit of corner, that's other stuff, right? Like carbon dioxide and other gases that are floating around inside the room. But that's where we get that percentage. But all the rest of this is empty space, okay? Letter C, they move independently of each other. So again, they're bouncing around like this. They don't move together like this around the room, right? All collisions between the molecules are perfectly elastic. I talked about that. The idea of dropping the ball on the floor and the idea that that ball goes down to the floor and comes all the way back up to my hand. That would be a perfectly elastic collision, right? So they don't lose any energy when they run into things. If they run into the wall, they bounce off of it with the same amount of energy that they went into it. They don't lose any energy. It's also considered to be the least dense form of matter. Least dense means if I look at one area of space, right, if I put a solid inside there, there's going to be a whole bunch of particles in there, which is a very dense area. There's a lot of particles per unit volume. If I put a liquid in here, if I put liquid water in there, it's going to be a whole lot of particles in a small amount of space. It's also very dense. Right? We would consider both of those to be a condensed form of matter. Condensed because they're all pushed together. Right? But then when we get to a gas, gases inside of this area, there's like a particle here and a particle there, and the rest of it is empty space. If it's empty space, then that means there's not very many particles there. So we consider it to be the least dense form of matter. Right? There's very little number of particles in that same amount of space. All right, so now a concept that goes with the idea of gas particles is a thing called pressure. And in class, I always joke about in class, I asked to see if anybody would be willing to run straight into a wall and don't stop. It's like, obviously, I don't have anybody do it, but I asked that in order to look at the idea, would that person exert a force on the wall when they ran into the wall? Yep. Would it be a lot of force? No, probably not. Right? Not meaning anything against that person, but it's just not a whole lot of force. It's probably not going to do anything to the wall. It's probably going to make the person like pass out, fall backwards, right? But it's not going to be a whole lot of force. Now, in the reverse of it, if we had everybody in the high school, all 400 people in high school, run right into a wall, is that going to exert a significant force? Yeah, reality is that's probably enough force that might actually knock down a wall, right? Because there's so many so much force between all 400 people. Same thing happens in regards to a balloon. My balloon out from underneath my desk. And in the case of this balloon, there are particles inside here, right? And they're bouncing around inside there, and they're running into the side of the balloon. Are they exerting a force? Yes, they are, right? If there was only one particle in there, well, then that balloon's going to look like this balloon right here. Right? This one, that's what it's going to look like if there's only one particle, because he's not going to exert very much force, right? But we got a whole bunch of them in here, and they're all hitting the inside of that balloon. So they exert a greater force. And because they exert a greater force, we end up with some pressure inside here. Now, what would happen if I take this balloon and I was able to pull out on the rubber part, the latex that it was made of, and make it bigger? And the same amount of air on the inside. Would they hit the inside of the balloon as often? No, they wouldn't. They would hit it less often because there would be more space. So what would happen is my pressure inside the balloon would go down because there would be less collisions. Now, to reverse that, if I take the balloon and I spin it, right, it pops. Did I pop the balloon? Nope, I didn't. I didn't pop the balloon. It was the gas particles on the inside of the balloon that popped the balloon. All I simply did was I took the balloon and made it smaller. And by making it smaller, I tightened them down so more of them hit the inside of the balloon. And as more of them hit the inside of the balloon, there was so much force that the balloon couldn't hold it, and it split the balloon open. So I didn't pop the balloon. The gas particles popped the balloon. So when somebody tells you, hey, well, you quit popping them balloons, you can go, well, actually, I'm not popping the balloons. It's the gas particles on the inside that are actually popping the balloons. All I'm simply doing is making the balloon smaller. It's an increase in pressure due to the condensing of those molecules, and that's actually why the balloons are popping. You might get the other person to go. Okay, so it's the particles on the inside. We make it smaller, greater pressure. If I make it bigger, less pressure because they're all spaced out more. All right, well, then it goes to a thing called, let me jump back for a second. Another thing that I also could do inside that balloon, I could keep it the same size, and remember that the motion of those particles is kinetic energy, right? Now, if I take that balloon that's the same size and I raise the temperature, I make it hotter, what are those particles going to do? They're going to move faster. If they move faster, that means they're going to hit the inside of that balloon with a harder force. If they hit it with a harder force, then the pressure goes up. All right? It's kind of like saying, for going back to that idea of a person, if I had a person walk into the wall, they're going to exert a little bit of force. Versus a person that sprints into the wall, they're going to exert a greater force because they're going faster. So if I raise the temperature of the particles, they have more force, more kinetic energy, and we raise the pressure inside. Now reverse of that, let's lower the temperature. If I lower the temperature, they're going slower. And if they're going slower, then they hit the inside of the balloon with a lot less force. And if you got less force, pressure goes down. All right. Okay, so those are two ways in which we can change the pressure. Make it smaller or increase the temperature. All right, a thing called atmospheric pressure. Atmospheric pressure surrounds us. All right, it's all the gas and the air that's surrounding us, and that pressure actually pushes in on us. And it's really the pressure from the collisions of air molecules in the atmosphere with the objects, like you. All right. And one thing that we do actually, in order for us to breathe, I don't actually suck in air. Really, what I do is I make my chest bigger. And when I make my chest bigger, I expand it out. Now there's less particles on the inside of my chest. And because there's less particles, it's a lower pressure. Now the air on the outside has a greater pressure, and it goes down inside my lungs. Right? Now when I go and I shrink my chest, what I've done is I've taken it and I've gone like this and pushed it all together. Pushing it together, I raise the pressure. And by raising the pressure, now it's greater than inside me than it is outside, and I go and I push the air out. All right. So it's really, I'm not, the way in which I like to describe this, there is no such thing as suction. You might go, no such thing as suction? Well, that's crazy. But there isn't. I'm not sucking in air. I'm making a lower pressure on the inside, and the air on the outside gets pushed in because of atmospheric pressure on the outside of my lungs. All right. A vacuum cleaner at home, what it actually does when you're sitting there sweeping the carpet, it actually removes the air from underneath the front of the vacuum. By removing that air, there's less pressure underneath the front of the vacuum, and the air on the outside goes and gets pushed inside. And anything that's in the way, including a sock, gets pushed into the inside of the vacuum cleaner. Right? So it's not sucking the stuff up. The stuff on the outside is actually getting pushed into the container. It's getting pushed into the vacuum cleaner. It's kind of a backwards on what we think. If you go to McDonald's and you get yourself a Coke and you take the straw and you go, well, I suck the pop up into my mouth. No, you don't. All you simply do is you decrease, you make your chest bigger, so you lower the pressure inside of your mouth and inside your body. And by doing that, what happens is the pressure pushing down on the pop forces the pop to go right up into your mouth. So it actually gets pushed into your mouth. Okay? So it's the atmospheric pressure that's forcing stuff into us. It makes us breathe. It makes it so that we can drink pop through a straw. Okay? If we don't have those, then we aren't going to be able to get that to work. And let me go get something. I'm going to pause for 1 second. I'll come right back. Okay, so I'm back. What I wanted to go get was these guys here, right? And what they are is they're little, I'm going to put it in quotes, suction cups. Now, I just told you there's no such thing as suction. Really, these things are named improperly, right? What I do is if I take them and I push them together, right? If I push them together, what I'm going to do is I'm going to push the air out of them. So I just push the air out of them. And notice now this other one's being held on there. Well, is it being sucked down on it? No. What's actually happening is there's no air on the inside, so there's a really low pressure in between them. And the air on the outside is trying to get in. It's pushing into it because it's low pressure on the inside, high pressure on the outside. And it's pushing on it and holding them together. How much pressure is that? It's a lot of pressure. Right? It's a whole bunch of pressure. Right? So again, if I don't push them together, notice if I let go, it falls. Right? But if I push them together, and I push the air, whoops, get them to go together, right? If I push them together, now there's no air on the inside, and now the air on the outside is pushing into it, and it's holding them together. So it's atmospheric pressure that causes these guys to hold together. It's not suction. There is no such thing as suction. All it is a lack of air, which causes a lower pressure, and then the outside atmospheric pressure pushes in. Right? So you can play with these kind of things. Go to the store and play with some toilet plungers at Walmart. My kids used to do that. They stick them on the floor and then go pull them off the floor. And really, when they're doing that, they're pushing the air out of them, and the atmospheric pressure is trying to get in. And when they would pull them off and go pop them off, it's actually the air going into that vacuum area. All right, which I'm going to jump down and say that's what's actually being produced inside here is an area called a vacuum. That area that's in between, that's a vacuum because there's no gas particles. It's empty space. And then what's going to happen in spots where there is air, that's going to try and get into that area. Right? That's why we call a sweeper a vacuum cleaner, because it utilizes a vacuum. It makes a vacuum underneath the front of the vacuum cleaner. And air tries to get in there, and anything that's in the way gets pushed inside. All right, now the last little piece, there's a thing about barometers to measure, and there was 3 units there. There is millimeters of mercury, atmospheres, and kilopascals. Those all measure exactly the same thing. They all measure pressure. It's kind of like saying pennies, nickels, dimes. But don't those all measure the same thing? They're all money, right? If I had 100 pennies, I got 20 nickels and 10 dimes. Is that not the same value? Yes, they all are equal to $1. So the same thing happens in this, is that, let me get